Hi, my name is Dan Low, and in this video, I'm going to show you how to prove A inverse equal to C transpose divided by determinant of A. And I use this notation to denote the determinant of A. Okay, and C is a cofactor matrix. Okay, so that's out. And A inverse, we assume A inverse exists. That means the determinant of A is not 0. So we start out with some notations. So let's see, I want to use the color green color. Okay, so let's say A is the matrix. Okay, and the matrix element is A11, A12, all the way to A1n. Okay, and that's the first row. The second row starts with A21 and all the way to AN1 and all the way to ANN. So that's the matrix A. Okay, so to discuss the cofactor matrix, we start with the minor. Okay, so the minor M, for example, M11. M11 is the determinant of the submatrix after you erase the row 1 and the column 1. So is the this is the M minus 1 by M minus 1 matrix. Okay, and then you find the determinant of it, and then this is the we use the M11 to denote it. So in general, Mij, okay, is the Mij is the determinant of the submatrix after we eliminate the ith row, okay, and the jth column. Okay, and then you find the determinant of it. So that's we call the minor. Okay. Next, we're gonna talk about the cofactor. Okay. So the minor, like M, I, J, is a determinant after we remove the ith row and jth column and find the determinant of it. Okay. And if we compute the negative 1 to the power of I plus j to find the sign, either positive or negative of it. And this one, we give it Cij. Okay, so Cij is the minor with the determinant of the submatrix with the sign, either positive or negative. Okay, and this matrix C is called cofactor. Okay, cofactor. And with the cofactor, then the determinant of A, okay, determinant of A can be described by, it's called Laplace expansion, by the A, okay, I j, okay, times the cofactor matrix Ij, and j goes from 1 to n. Okay, so it's called Laplace expansion. Okay, so and for all, this is for I equal to 1 to all the way to n. Okay, so let me give you an example. Like you have 1, 2, 3. Okay, and then 1, 1, 2. Okay, 2, 2, 1, something like this. Okay, so the determinant of this, okay, it can be doing like you pick this row, you set I equal to 1, and this 1, okay, times the sum matrix, which is this guy, after erase row 1 and column 1. So it's 1 minus 4, it's negative 3. And since this is positive, okay, and because negative 1 to the power of 1 plus 1 is positive, okay. And second thing, you pick this one, 2, okay, plus 2, okay. And now you need to put a negative here, because negative 1 times here this is 2, the 2 plus 1 is 3, okay, so it's negative. And then after you remove this 2 rows, then 1 times you got a 1 1 2 2, so 1 minus 4, so that's negative 3, okay. And lastly you pick up 3, okay, so you also positive 3, okay, times 2 minus 2, 2 minus 2 is 0, so this one is gone, okay. So altogether this is negative 3, negative this is negative 1 and negative 3, so it becomes positive 6. So the result is 3, okay. So you can verify this by another regular way. You compute the determinant, so it's 1 1 1, it's 1 plus 1 2 3 is 6, okay, and plus 2 2 2 is 8, minus 3 1 2 6, okay, minus 4 and minus 2, okay. So here you get 6 cancel out, and then and 8 plus 1 is 9, 9 minus 6 is 3. So that's basically the Laplace expansion is all about, okay. So with that, then we now know we have the determinant can be described by this Laplace expansion form, okay. So in order to prove a minus a inverse is equal to c transpose divided by determinant a, so we can go ahead to a multiplied by a inverse should be a equal a minus equal to a multiplied by c transpose divided by a, okay. If you can somehow do this, verify this equal to I, and then we done that a inverse is c transpose divided by a, determinant of a, okay. So now we have we want to verify a, okay, time multiplied by c transpose divided by determinant a. We want to verify whether this is identity matrix, okay. So we start with a11, a12, okay, all the way to a1n, and then this is an1 all the way to ann, okay. So that's a, and then we got the determinant a is a number, scalar, so we can put it anywhere you want. And c transpose is c11, c12 all the way to c1n, okay, c21 all the way to cn1, then cnn, okay. So that's the c transpose. So this is c transpose, okay. C transpose is a nickname called educate of a, educate, also ADJ A, okay. So this is educate of a. So now if we do that, now we want to verify whether this is equal to identity matrix. That means all the diagonal elements are 1 and the rest are all zeros, okay. So we start check the first one. So the first element is coming from the row 1 times column 1. So the row 1 times 1 is A11 C11 plus A12 C12 plus all the way to A1n C1n. Okay, and don't forget you have a constant scalar here, so divided by A transpose. Okay, not transpose, A determinant. And if you look at this is A11 C11 A12 C12. Okay, so you go back here. If you let I equal to 1, here you put I equal to 1. Okay, so this is the A11 C11 A12 C12 all the way. Okay, so that is actually the summation of A1 J. Okay, and then C1 J. Okay, J goes from 1 to n. Okay, and this is actually determinant of A. But now we have determinant of A divided by determinant A, so that will be equal to 1. So we verify this is equal to 1. So in general, okay, if you are doing a diagonal, which is the index are the same. Okay, the the A1 A1 1 C1 1, if A21, that is the second row. Okay, the ith row and the jth column, if I and j are the same, okay, in a diagonal, then you have the value 1 on the diagonal. Okay, so the diagonal is done. Now how about this, the zero part? Okay, the zero part means I and j are different. I and j are different, so that means you pick ith row and jth column time together. Okay, and then that must be 0 if I not equal to j. Okay, so if we do the matrix multiplication, we pick ith row of A because we have A, right? We use A, okay, multiplied by C transpose, okay, and then divided by this, right? So if we pick the ith row of J, ith row of A, times the jth column of C transpose, okay, then we want to show that result is 0. Okay, that result is 0. Okay, so so here to show that let's start with this. Well, we'll first write it down. Okay, so the ith row, okay, ith row J, ith row of A. Okay, so you have A ith row, okay, ith row of A. We use K, okay, AIK, okay, and times C transpose. So C transpose, we actually the jth row of C transpose is start with C, the jth row, right? C J1, and then C J2, okay, to C Jn. That's the the jth row of C transpose. Okay, the jth row. Okay, so that we times that number C, okay, and then J, okay, and then K, CJK, CJK, and then we sum them together, so K goes from 1 to N, okay. This is I9 equal to J, okay. Now let's create another matrix from A called A prime. So A prime is a matrix created from A. So you have A11, A12, all the way to A1n. Okay, but this is the ith row of A prime, also from AI1 all the way to AIN. Okay, but the jth row of A prime is a copy of ith row, so it's AI1 all the way to AIN and all the way to AN1 to ANN. Okay, so this A prime is derived from A, only differs in the jth row. The jth row is a copy of ith row, so it has the two row identical. So according to the determinant property, the two rows the same in the matrix. The determinant A prime is 0. This is 0. Okay. So because determinant of A prime is 0, and then now we use the Laplace expansion on the jth row. Okay. So based on the Laplace expansion on jth row, the determinant can also be described by summation. Okay, on the ith row. So in jth row. Okay, so it's A I K, okay, yeah, K, okay, times the cofactor matrix is CIK, okay, no, CJK, the jth row, so it's JJ, okay, and then K, so this is C prime, the cofactor matrix of A prime, and K goes from 1 to N, okay, and we argue that C prime JK, okay, is equal to C JK because when you remove this jth row, okay, to compute the minor is identical, okay, it's identical to the original CJK. So this is also equal to summation K goes from 1 AIK to CJK. Okay, and what is this? This is right here. Okay, so that's also equal to 0. So that's equal to 0. So now we prove that as long as I not equal to J, then all those elements in this multiplication will be 0. So that means, A times C transpose, okay, divided by A determine its identity matrix. And there, because of that, so A inverse is this part, okay, it's equal to C transpose divided by determinant A. So that concludes the proof. Thank you very much. Have a good day. Bye bye.